After having completed the anti-entropy part, now we discuss the rumor mongering, okay? And about the names, they are just nice names and they do not carry very important meanings. They are just labels that we use to discuss these approaches because why this refer just to rumor is just a matter of opinion. But the idea is the following. Nodes are initially susceptible. And when a node receives a new update, it becomes a hot rumor and the node is infective. A node that has a rumor periodically chooses randomly another node to spread the rumor, as before. But the difference is that a node will lose eventually interest in spreading the rumor and becomes removed. So the idea is that you may have, I don't know, a rumor about Chiara Ferragni, and then you go around and you say, do you know the latest news about Chiara Ferragni? And you say it. But you can do it once, you can do it twice, and at some point people will start to say, okay, I already know this, and then you may stop. And the reason to stop, there are a lot of reasons to not talk about Chiara Ferragni, but the reason to stop is that you have spread this information too many times, or everybody already knows the rumor. Everybody that you contact already knows the rumor, okay? At this point, a sender can hold and transmit a list of infected updates rather than just one. So collect a lot of them, a number of them, and send them around, okay? So the idea is the following. The important part here is the loss of interest. So you have to decide when and why losing interest in spreading the information. So when could be counter versus coin. Coin means random. So in coin, you lose interest with the probability 1 over k, where k is a parameter of the protocol, and you lose after you send a message, you lose interest with this probability. Or counter, you lose interest after a given amount of contacts that you have. And then there is the why, okay, which could be feedback or blind. So you can lose interest only if the recipient knows already the rumor, and this is feedback. So I send you a message in a push way, you reply with something like already knew it, and then I can feel that it is time to stop. Or you can be blind, you lose interest regardless of the recipient. So what you see here is rumor mongering push with a blind coin variant, but you could potentially have 4 different variants based on blind counter, blind coin, feedback counter, okay? So the idea is that you start in an affected situation. This is your state. You have a value which has been updated by an update operation, and you set a timeout periodically, and then you reset the timeout. If your state is infected, then you select a random node, you send a push value to Q, and then this is a blind coin, means that irrespectively of the state of the receiver, you do not expect a reply from the receiver, you toss a coin with the probability 1 over k, and if the toss coin replies true with the probability 1 over k, your state is removed. And when you receive push, if your state is susceptible, you go to infected. If your state is infected or removed, you do nothing, and you update your value. Again, we are considering one single value here, but add some code and consider a list of values and list of updates. And this instead is a feedback counter variant in order to show you a completely different approach. And so you have this counter k, which is a counter pair. There is a different counter per every entry, but here we have just one entry. Okay, the timeout mechanism is the same that brings you here. If your state is infected, you send a push to a random node, and that's fine, simple. When you receive a push and you send a reply with your state to queue. So if you are susceptible, if you are removed, if you are infected, you send a reply. If your state is susceptible, you tell this to you update, sorry, your local value, and you become infected, and you put your counter equal to k. Whenever you get a reply, and remember, we are considering a feedback variation, if the reply is different from susceptible, is either infected or removed, this means that you have received a feedback from someone who already knows the information. So counter is equal to counter -1, and if counter is equal to 0, you go to removed. Very simple, I think. So, how fast does the system converge to a state where all nodes are not infective, an active state? We use comportamental analysis again, for example, for feedback coin, but remember, you should use 4 different analysis for every kind of system. And what we get here, I don't want to enter into the mathematical details, is that you're using differential equations. You have 3 populations, like S, the set of the fraction of susceptible, infective, and removed node, SIR. The various fraction add to 1, clearly. And then the rate of change of susceptible is the fact that whenever you do whenever you change from you become susceptible if sorry, you stop being susceptible if you were susceptible before, and this is feedback coin, you have contacted an infected node, and minus because the number of susceptible nodes is lower during the execution of the protocol. Then you have this part here, which is the opposite of the fact that someone is becoming infective because it's contacting an infected person. And you have instead a negative variation, which depends on the fact that someone goes to removed, which is given by this probability here. You have to be infective to become removed, and you have to contact someone which is not infective, which is not susceptible, 1 minus S, and then you have this feedback coin, you have a probability 1 over K to become not become removed. Sorry. You solve the differential equations, and you get something like this. S is equal to E power to minus k plus 1 times 1 minus s. What I want to underline here is that increasing k increases the probability that the nodes get the rumor, clearly. The smaller 1 over k is, the larger is the probability that the nodes receive the rumor. And the reason I'm telling this is that it is possible in this particular approach that at some point the nodes that are susceptible, have not become infected, have not become removed, are different from 0, and the protocol has stopped because everybody else is not infective anymore, has become removed. Okay. Uh, the idea is that we can compute a residue. A residue is the number of nodes, the fraction of the nodes that remain susceptible when the epidemic ends. The value of S when I is equal to 0. Clearly, we would like to have a residue which should be as small as possible. Okay. And the traffic, this is how we measure, how we evaluate these protocols. The traffic is the average number of database updates sent between nodes. So the total update traffic divided by the number of nodes. The convergence, which can be measured in two ways. The average time it takes for all nodes to get an update, and the time it takes for the last node to get an update. Note that some of the nodes, because they are in the residue, might never get an update. They are not computed on the average and on the max, clearly, because otherwise we should consider them as infinite amount of time in order to get the update. So this gives you um, an idea of how it works. These numbers are almost similar to the numbers that you see in the original paper, because I try to reproduce them by myself. There are very small differences. And the idea is the following. We are using here blind coin, so the first set of slides that are shown to you. And the K goes from 1 to 5, and the residue here is the probability of remaining susceptible, so to not receive an update. The smaller, the better. And you can see that even with values like 5, which is very, very small, you get a probability which is less than 1%. Clearly, increasing the number to 10, etc., can provide you a much better value. The average traffic is slightly less than 5, because some of the nodes stop earlier. And the delay, if this is measured in number of rounds. So the number of rounds that it takes to spread the information around. So you see here that you have a T average around 13.8 and a T max around 32, which is quite a lot, but this is not the best protocol that you can use here, but giving you an idea of what kind of number of rounds we are talking about. If I remember correctly, this was a network of 1,000 nodes, so really not very large for my standard, but clearly you see that with a very low amount of traffic, you can get a very robust communication. This is much better. This is a feedback counter, same kind of parameters, and you get a probability which is much smaller. Over 1,000 nodes, it means that one of them may not get an update. The traffic is slightly larger, but also the time, in particular Tmax, is smaller. Okay. So far we have assumed that we are using push because if the database becomes quiescent, so stops being injected with updates, the push stops trying to introduce updates. Pool, if there are many independent updates, pool is more likely to find a source with a non-empty rumor list. But if the database is quiescent, several update requests are wasted. Okay, and so this is what you normally use, which is a very good idea to use. Normally, what you can do is a very quick and dirty push rumor mongering, which means that you use push to try to spread as much as fast as possible your information with low traffic, and still there is a non-zero probability that some of the nodes remain susceptible after the epidemic. And then you run on the background much shorter, much longer um, round length. You use a push-pull anti-entropy protocol can be run very infrequently, a second, 1 minute, in the background to ensure that all nodes eventually get updated with the probability 1, which is something that is guaranteed by anti-entropy. From now on, I can talk about the nifty details of this particular protocol more or less forever, because there are a lot of improvements that you can do in this kind of protocols. And really depends on the kind of system that you have in mind. And I don't have a very definitive formula to design something like this. But we can have a look at some of the issues just to have an idea. So, for example, deletions. If you want to remove an entry, I mean, removing a key value association in the dictionary that is stored by the replicated database, you cannot just removing it from a node because the absence of the entry currently is not propagated. So if there is an update, then you get the new entry and the deletion is not considered. So you may use a death certificate that has a timestamp and spreads like an ordinary update. So you have these um, death certificates that are stored in your system. The key one is not used anymore. Uh, Clearly, at some point, your database will be full of death certificates. So what you do is that you may have a couple of strategies. One could be to try to collect information about the fact that every other node has received the death certificates. This requires another protocol, somebody does that, but it's very, very complicated, and you have to handle node failures and so on. The strategy that is used is to hold death certificates for some time, like 30 days, 60 days, and discard them in a very pragmatic approach. You may still have some sort of resurrection problems, and increasing the time requires more space, but it's a very pragmatic and simple solution. Okay, and let's keep this. If you want to transform this into a broadcast, because sometimes you have seen this, sometimes I speak talking about updates, sometimes I speak talking about messages. The point is that they are more or less the same. So your database could be a collection of messages received, um, and in anti-entropy, this means that you have to run a mechanism to check if you have more up-to-date information about messages. Okay, and this more up-to-date information means that maybe the timestamp could be a vector clock in order to see if you have all the information about messages sent by all the potential members. Vector clocks could be very large, so there is an entire area of research about compactifying, reducing the amount of size related to how vector clocks are stored and sent around in the messages. Uh, if, if you're using rumor mongering, then an update is equivalent to a message broadcast. And if you are using both of them, the idea is that you have the database and the push protocol that sends the message around in a very quick way. So what next? There are a lot of issues here that we have not considered in a very detailed way. So the first issue is membership. How the process get to know each other and how many do they need to know about themselves. So the point is, remember the original situation. You have one single company, Xerox, that was managing a set of branches. This is the idea of having 1,000 databases, okay? And all these branches have their own copy of the database. A single company could update a list of the branches whenever there is a new branch. But this means that this doesn't happen very often. And this means that you can update the list by using the same mechanism of communication, by sending through push to anti-entropy the list of nodes. So some points you get, instead of 1,000 branches, you get 1,001. And you add this information to your list of branches. What we are going to see in one of the next lectures is the fact that you do not need to know the entire list. Carefully selected subset of the entire list is sufficient, and this subset could be dynamic, so change over time. And this means that instead of, if you have 1,000 or 1 billion or 1 million nodes around, instead of knowing the entire list and have to update it whenever there is a change, you need a much smaller list. It could be as small as 20, 30 entries, even if the network has size 1 million, okay? But that list could be up to date, so it could contain nodes that are current in the network. So if your network is dynamic, some of the nodes need to be discarded or forgotten, and some of the nodes need to be inserted in this particular list. Okay. Network awareness. These protocols tend to send messages around without caring about the fact that maybe one node is in China, one node is in the United States, another node is in Europe. So the idea is that you may want to focus your communication to more local set of connections. And this could be obtained, for example, by selecting the nodes that are closer to you, for example, in terms of latency. This is something that Bitcoin does continuously. Instead of just communicating with every other node, try to communicate with nodes that reply quickly. If they reply quickly, they are probably local or more local than some very distant China node. Okay, and the last part, which is not covered in my lectures, but you can look at the references in the document that I'm giving you at the end, is buffer management. The fact that if you're using push and you are sending information around, if there are a lot of updates, as someone was commenting, the idea is that you can get a lot of traffic. So you may want to select some of the updates that you want to move around based on the amount of traffic that you have. Okay. And as I said, epidemic concept approach has been successfully applied to other problems, and we will provide an overview of that. Okay. So, what to read? Have a look at the original paper, but it's a paper of 1987. The only copy which is around is a scan of the original paper. It's not very clear to read. I mean, typographically speaking, the paper is very, very nice. And then there is this one, which I've been asked to write. This is a summary of 3 years ago about gossip and epidemic protocols. The second one includes also the part that we are going to cover in another lecture, so don't be scared by the length. Okay, and that's it.